I'm Paul Den Hout. I'm a senior lecturer in the School of Chemical and Metallurgical Engineering. This is a course in practical metallurgy, and any course in practical metallurgy identifies properties and then finds a way to measure that property. The measure of how ductile and brittle a material is determined by how it responds, or the amount of energy that it absorbs when it's subjected to an impact. And the test for doing that is the Charpy impact test. We'll be looking at 4 materials today: aluminium, copper, mild steel, and brass. Let's consider for a moment our first year physics. You'll remember that there are 2 types of energy, potential energy and kinetic energy, and that objects placed at height have potential energy that when they fall down or when they roll down, that potential energy is translated into kinetic energy. That's exactly what happens in the Charpy test. Let's see how that translates. What we have as our object, the one that carries the potential energy, is the hammer. And you see it here, it's in the lowest position now. So when that is placed and locked at the high position, it carries a considerable amount of potential energy because of its mass. When it's released, it swings down, and as it does so, the potential energy is translated into kinetic energy. So that at the bottom, it has its maximum kinetic energy. And that's at the point at which it hits the test specimen. It continues through to a certain height. And the difference in height, or the difference in potential energy, must then be the kinetic energy that was absorbed by the test piece. When it hits the test piece and swings to the top, the position that it swings to is indicated by this scale over here. And this has now been calibrated to give it in joules, in other words, the amount of energy that has actually been absorbed by the test piece. That scale gives it to you directly. Here we have a copper test piece. All test specimens are made to fixed dimensions. That's a requirement of the test. What you see is in length, it's 55 millimeters. In cross-section, 10 millimeters by 10 millimeters. At the center on one side is a notch. The notch is 2 millimeters deep, and it's set at an angle of 45 degrees. And the tip of the notch, the radius, is 0.25 millimeters, 250 microns. Right, the first thing we have to do is to get the hammer into place. So we need to start swinging it and bring it up into position. When the hammer is in position, we make sure that the safety hatch is on, so that anybody working down at the bottom will not be injured. And now it's in position, and what we do is to move this needle across to its maximum. The first piece we'll test is mild steel. We position it in the instrument using this clamp. It has a notch on one side, and the notch must fit into the groove that we have in the test piece. And what we then do is to place it in the instrument. Right, when we've secured the place, nobody's standing in front of the instrument, we release the safety latch. The test piece flew out in front of the hammer. Once we've secured the hammer, we can recover the test piece from the ground. And here you see the one for the mild steel. That's fractured. Now begins the second part of the test, and that is to examine the fracture surfaces. It tells us a lot about how brittle or how ductile the material is. There's one last thing that one would do in a test like this, and that is to record the temperature of the test piece. Because this is at room temperature, we can record with a thermometer what the room temperature is. Temperature is important because for the same material, very cold temperatures, material will display brittle behavior. At high temperatures, it'll be ductile. Right, we're placing the aluminium test piece in position. We then secure the gate. Everybody cleared from the front. We release the safety hatch. And now we'll notice that the amount of energy is less than 20 joules, 18 thereabouts. So far less energy absorbed by the test piece. Right, we've secured the test piece. We've moved the needle to its maximum. We then release the latch and this one is even more brittle than the aluminium. You'll see it's less than 10, about 7 joules. Right, with our test specimen, this one is copper, the last one. And we release the safety latch and now we see that the needle has moved to probably 112, thereabouts. Here we have the 4 test specimens after the test. I've ranked them from the most ductile to the most brittle. Most ductile, the mild steel, going through to copper, to aluminium, and to brass. In these measurements, if you were to repeat them, you will never get exactly the same value, the number of joules that we measure on the instrument. So what's usually done is the test is repeated, and you find that you get values that vary about a mean. Now that's not an error, that's an uncertainty. And you would generally take averages and you can work out standard deviations and so on. But that's the last thing that one would do. So this test would be repeated sometimes 4 times for each material. And that concludes the practical.